in Leuven, just outside of Brussels, scientists have gathered to talk about the weather. But not the rain or cloud cover of terrestrial weather, but the geomagnetic storms and solar winds that are part of a larger topic, space weather. So what is space weather? Fundamentally, the term refers to the changing environment in space caused by the dynamic behavior of the sun.
Like the weather on Earth, our sun goes through an activity cycle that has an 11-year-long duration, and this activity cycle is related to sunspots that are visible at the surface. And as the activity rises, we see more sunspots, and as the activity falls, we see less sunspots. So sunspots are dark regions. They have a very high, very strong magnetic field, and they are the sources of flares. Flares are increased electromagnetic radiation that is able to send particles through interplanetary space. Radiation reaches Earth in about 8 minutes, and they're also coupled to coronal mass ejections, or CMEs, huge plasma clouds and magnetic field that can propagate also towards Earth and reach Earth within a day or two, depending on their speed, and they can cause a lot of effects that we call space weather.
Solar flares and CMEs are sometimes associated with solar particle events, in which electrons, protons, and heavier ions are accelerated to near light speeds, potential radiation hazards for astronauts and damaging to satellites in space. As charged particles from the sun strike and interact with Earth's magnetic field, they create the beautiful aurora most commonly found near the North and South poles. In the background of these spectacular solar events is the ever-present solar wind, a flow of electrons and protons that constantly streams out of the sun in all directions. Traveling at about 1.5 million kilometers per second, this wind is always interacting with Earth's magnetic field, giving it its characteristic shape, compressed on the day side and stretched to a long tail on the night side. Our planet has lived alongside the mood swings of our star for billions of years. However, the way we live has changed dramatically in recent years as we become increasingly dependent on infrastructure we've built in space and on the ground. So things like communication networks, satellite navigation systems, and electricity grids are vulnerable to solar events that cause storms in the magnetic field around our planet, called geomagnetic storms. In 1859, a giant coronal mass ejection caused one of the largest geomagnetic storms on record, the Carrington event. A white flare was observed by astronomers, and auroras were seen as far south as the Caribbean. The sky was so bright in the middle of the night that it woke gold miners in the Rocky Mountains, who began preparing breakfast as they thought it was morning.
The telegraph engineers witnessed sparking from the telegraph, and they witnessed when the whole thing was turned off, it was still actually powered. So messages were still being able to be sent and received. So they didn't understand what this was and why this was, but it was reported as an incredible phenomenon.
In 2012, a storm of similar magnitude was observed erupting from the sun, but fortunately missed Earth by 9 days. It is estimated that a Carrington-like event today would cost €16 billion in social and economic damage to Europe alone, with widespread electrical blackouts, interference with radio communications and navigation systems. So how can we protect our planet from events like these? The first step is accurate monitoring of the sun's activity. For this reason, ESA is planning to send a satellite to a unique position in space, the 5th Lagrange point, where the gravity of the sun and Earth interact in such a way they create a stable gravity plateau. From here, the Lagrange satellite will get a side-on view of our star and the space between it and Earth, detecting hazardous solar activity before it reaches us and estimating its time of arrival and potential impact. The satellite will work with the planned U.S. mission to the first Lagrange point, and together, these two missions will provide an unprecedented near real-time monitoring of the sun.
The data from the Lagrange mission is going to be sent down through the ESA deep space stations to the ESA's space weather service network. These services will be used by European governments, civil protection authorities, operators of various elements of the infrastructure, including satellites, power systems, transport. And this will allow people to take action to mitigate space weather impacts and protect our infrastructure from the adverse impacts of space weather.
Extreme weather events are rare, but they've happened in the past, and they'll happen again. As technology advances, the disruptive effect of solar storms is likely to become even greater. This is why ESA is working to monitor our raging star, providing the information necessary to protect our satellites and vital infrastructure.